All right. Well, thanks, Helen. That was really fantastic. Great way to kick off. And now, because we've had several segues into Peaks Range and rare earths, we're going to hand over to Stewart Parker, who's going to tell us about the work that he and the Northx guys have done in collaboration with University of Adelaide and CSIRO to develop that area. So take it away, Stu.
Thanks, Helen. I've just got to find my PowerPoint here. Okay. Well, in 2018, while looking at other rare earth occurrences in northeast Queensland, Northx was very fortunate to learn of the peaks and the critical minerals lava domes. This was a discovery made by JCU University student Ross Chandler and his supervisor Carl Spandler. Are you able to hear me all right, Helen?
Loud and clear, Stu.
Terrific. Okay. This area that we're looking at is around about 30 or 40 kilometres to the south of Fletcher's Hall that Helen's just talked about. The prospectivity was discovered, as I said, by Ross, and in 2018, and Northx was fortunate that they were in the right place at the right time and heard about his identification of these areas, and we were able to secure an EPM over it and form a partnership with Ross and Carl to further explore these very unusual volcanics. While Northx holds a tenure, the understanding of the geology researched by Ross and Carl is the foundation of this project. They identified the field of very highly fractionated peralkaline lavas that form a rare group of porphyry rare earth prospects in the Southern Peaks Range. And they're shown in this little boxed out area here. These rhyolite lavas contain highly anomalous levels of rare earths and other new economy minerals, including zirconium, hafnium, niobium, tantalum, gallium, beryllium, and even lithium. Similar and better levels than those reported from the USA's largest rare earth porphyry deposit, Round Top, in Texas. Ross and Carl's work showed that this group of critical minerals were at significantly enriched grades in a very highly fractionated field of visibly different pale green lava domes that were enriched in the sodic pyroxene mineral agerine. Rock samples, in fact 10 rock samples from 4 of these agerine enriched domes were sampled, and they're shown by those 4 red little circles I have on my screen, and were used by the CSIRO in their characterisation study. A further subvolcanic breccia sample, as shown by this little star here, was provided as a slightly different rock type to compare the results. Initial mineralogical work by Carl and Ross in 2018-2019 had identified several of the high-value minerals, including eudelliite and dallite type rare earths. These were associated with the agerine, with feathery zircon, silicates, and with a zircon gel mineral. These high-value minerals were also partly associated with clays that indicated the potential to be easily leached. In early 2020, Northx asked the CSIRO's Hydromet Group leader, Keith Bernard, for help to explore bulk processing options for the Peaks lavas. Keith pointed out that the first step was to look further at the rare earth and high-value metals mineralogy and the groupings before considering any processing options. Keith proposed a more comprehensive characterisation study, which would then be used to inform on the more likely processing routes to scope. It's this characterisation study that the GSQ have supported through our 40,000 grant. The characterisation study was undertaken over a 6-month period by Drs. Robbie McDonald and Dr. Peter Austin, also from the CSIRO's Hydromet group in Perth. The study was completed last month in late May. Northx provided the CSIRO with 11 100 to 120 gram samples. These had all been prepared to minus 250 micron. They came from those 4 domes I showed earlier, plus that subvolcanic breccia pipe. The aim was to provide some diversity in the lavas rather than just target the highest grade sites. So we're not just reporting here on Christmas Dome or Clary's Dome, but on 4 different domes. All 4 domes were of A-green bearing lavas. The breccia pipe was quite different. It included a mix of both basic to intermediate and felsic subvolcanic fragments. We completed multi-element assays for around 43 elements and provided that data with the CSIRO. The summary table of these analysis shows the highest grade rare earths were from Clary's Dome down here. They represent rare earths of about just over 0.3-0.4% total rare earth oxides. The Christmas Dome samples also contained high heavy rare earths. The heavy rare earths I've highlighted here in darker blue, light rare earths in pale blue. But the Christmas Dome samples also had the highest zirconium, hafnium, gallium, beryllium, and lithium. And some of these were taken from a central dome site. So we know that these metals are distributed right across the dome rather than just in select places such as the dome margins, where we particularly know that we're getting good metal values. The Woolbale Dome, which is about 10 kilometres to the south of Christmas and Clary's Dome, had the highest niobium and tantalum, about 1,000 ppm combined niobium and tantalum. And the Pitts Dome, which is to the north of Christmas and Clary's Dome, had the highest phosphate. So we had a spread of 4 quite different or slightly different geochemical signatures for our metals. The CSIRO mineralogical characterisation analysis was completed by 3 methods: X-ray diffraction, quantitative X-ray diffraction, XRD or QXRD, quantitative evaluation of minerals by scanning electron microscope or QEMScan, and scanning electron microscope with energy dispersive X-ray spectroscopy SEM-EDS techniques. One of the key aims of this project was to identify minerals that were rich in the rare earth elements and or contained rare metals that included the zirconium, the hafnium, the niobium, the tantalum, and the gallium. Unfortunately, the standard QEMScan analysis could not be used for this purpose. The mineral grains identified as containing most of these elements, with the exclusion of gallium, were generally too small. There was also a significant overlap of these high-value metal grains with the major minerals, both at the grain edges and beneath the grains. Due to their very fine grain size, the CSIRO undertook a novel SEM-EDS approach. They selected multiple grains to identify many of the high-value minerals assemblages before reprocessing them with the QEMScan. This approach was the key to identifying many of the high-value mineral groups. And I've got just a couple of examples there on the right-hand side of that work. Using the QXRD, the major mineral compositions were obtained for the 10 rhyolite lava dome samples. All had high quartz, ranges between 28 and 36% quartz. All had albite and orthoclase feldspars, but in 3 samples, much of the orthoclase had been supplanted by microcline. All samples had between 10 and 16% agerine. Muscovite, kaolinite, and actinolite were minor minerals. As I said, the bulk compositions were obtained by QuemScan. The results showed that for all the lava domes, the bulk compositions were fairly similar. So each of the lava domes I've identified here. The only one that's not a lava dome is this sample 21. That's the bimodal intrusive breccia, which was clearly quite different, having lower quartz and higher clay, among other things. Bulk mineral composition phase mapping, like this one for the Woolbale lava dome in the southern part of the tenement, gave an indication of just how disseminated and fine-grained the high-value minerals are within the zircon, rare earths, and agerine. This also illustrates why these lavas are considered a porphyry style of rare earth. And you can see the scale bar here, if you look at the agerine crystals or minerals in bright pink and red, they're all less than 50 microns in size, and they generally were mapping out most of the other high-value rare earth minerals. So in terms of results, the SEM-EDS analysis indicated 2 types of zircon were present. One containing rare earths with low thorium-uranium levels at detection levels below the methods used. The other containing 5 to 7% yttrium, as well as detectable amounts of other heavy rare earths plus uranium and thorium. Zircon oxide, possibly as badallite, was also inferred to be present. Grains rich in niobium and containing silicon were also identified. However, they didn't indicate a known niobium silicate mineral. One plausible explanation is that these niobium grains consist of an intimate mixture of minerals, which may include a rare earth rich pyrochlore mineral. The EDS inferred rare earth rich mineral grains consistent with rare earth carbonate minerals, likely basnasteite, rare earth phosphate minerals, likely monzonite, and a mixture of yttrium phosphate oxide, xenotime, and yttrium arsenate oxide, xenovite, probably as a solid solution. Rare earth manganese minerals, likely a solid solution of barium manganese oxide, hollandite, and the lead manganese oxide, coronadite. All of these contain significant rare earths. Grains rich in cerium and lanthanum, among other rare earths, were also identified, but have yet to be assigned any minerals, to any likely minerals. For the current study, elements that included lithium and beryllium were not examined, as they required more advanced and costly techniques. The table on the right shows the identification of rare earths, niobium and zirconium minerals and their compositional groupings by SEM EDS QuemScan for two similar Christmas lava dome samples. Both samples show a high proportion of rare earth carbonates, zirconium yttrium silicates and cerium silicate minerals as the major value minerals. Similar analysis was done for all the samples. The SEM micrograph on the left-hand side shows a scan of the rare earth carbonate within a composite of quartz, feldspar and adrine minerals in the lavas. The mineralogy variation of the rare earths, niobium and zircon minerals and their compositional groups between all 11 samples using the SEM EDS QuemScan is illustrated in the bar graph on the right. The graph shows most of the rare earth carbonates in blue as a significant mineral component. Two samples have rare earth phosphates, and they're shown in that browny orange colour, as their most important rare earth component, while zirconium mineral compositions were quite variable between the samples. The characterisation study has meant CSIRO have been able to further support Northx through their Kickstart research program. These results have been used to support a preliminary processing study looking at the recovery of the high-value minerals by acid leach. This current study has been a direct consequence of the GSQ's CEI funding. Preliminary results suggest that a modest acid leachate has the potential to extract well over 90% of the rare earths from these lavas. The GSQ have also supported further alternative processing studies funded through work by the UQ Sustainable Minerals Group, and we're looking forward to further encouraging results from that work. Thank you to all those who have made this possible. I'd especially like to thank Ross Chandler, Carl Spandler, Robbie McDonald and Peter Austin and Keith Barnard, plus the Geological Survey crew who have made this possible. Thanks, Helen.
Thanks, Stu. That's fantastic. What a sort of a really integrated study, which really shows the value of mineralogy in understanding these rocks, which are already pretty complicated in terms of, how do you even get rare earths out of rocks like these? So understanding, are they silicates? Is it in monazite? Is it in xenotime? I think is crucial, as you know. We do have a few questions for you, if you don't mind.
Go ahead.
But feel free to pass them on to CSIRO if you need to. So,
good idea.
Ken Collison is asking, was saying that the multi-element data that you presented was obtained by 4-acid dissolution and ICP-MS. However,
look, we did several different techniques, so I did only show down a cut-down version of that. We certainly did the 4-acid digest MS analysis, but obviously that doesn't work very well for elements like fluorite and chlorine and some of the other metals. And for things like zirconium, we get very low assays using the 4-acid digest, so fusion techniques were used to get those sort of analysis. So we're getting analysis for instance, for zirconium of just 300 to 500 ppm with a 4-acid digest, and 4,000 to 5,000 ppm using a fusion analysis.
Excellent. Well, that was the rest of his question. So, did you use fusion, dissolution, and what was the comparison? So, perfect.
Yes.
Perfect comparison of techniques and the importance of understanding your rocks in order to choose the right technique.
Yeah. So look, obviously we had pretty much a full suite. There was a fairly costly analysis. Each rock was about $150 worth of analysis before we started.
That's what you got to do, right? So, well, I'm going to jump a question and go to Mike Whitbread, who has, following on from that, rare earth recovery. What were the rare earth recovery values in the fusion versus 4 acid? So you've given us the zirconium example.
Yeah, look, I can't answer that yet. That's an ongoing study. Those results I showed you were just some preliminary H2SO4 leach tests with a low, I think it was 40 molar acid leach, and they obviously, I think the average recovery was about 95%, but they're very preliminary, and so we haven't. The rest of the study is still ongoing, and I'm expecting those results in the next couple of months.
Okay, and Ken has asked the same question, so we'll click that one as done. Nick Oliver is being a smarty pants and saying, don't forget to mix Coca-Cola with your aqua to get full dissolution. Thanks, Nick.
I'll try that, Nick. Good idea. I like Coke.
Pat Heyman is saying, very interesting. Has there been any work on the controls of physical volcanology or the controls that physical volcanology may have on rare earth concentration? For example, proximal to dome versus distal settings.
Look, all these samples are surface samples. We're hoping to do the first drill hole on one of those domes later this year, in the next couple of months, maybe. We've done a lot of potable XRF sampling across the domes and also the intrusive sediments that are around them. And the moment we walk off the domes, there is very little in the way of anomalous mineralogy outside the domes.
Okay. Nick says he's been playing too much with aqua region data. He also would like to know, is there any geophysical suggestion of possible anomalism that might lead to higher rare earth concentrations?
Look, radiometrics are critical to these domes. They're obviously, they're high in potassium, they're high in thorium, they're high in uranium. Some of the initial sampling used a scintillometer to just select samples that had high total count. We've actually found, after using a portable XRF that we're not using with a scintillometer, that we're getting some very significant values that aren't necessarily associated with the higher radiometric anomalies as well. So radiometrics lead you into the target area. They don't necessarily show where the best mineralization is. Magnetics, I think, aren't at all useful, certainly not at the scale that we have available, and gravity is not much good either. But I think at a closer space, seeing obviously geophysical techniques might be very useful. There are some structures in there that we don't really understand, and they probably will give us some upkick in all the metal values.
You need some of the resolution that Helen was showing us in
exactly.
the last talk.
I wish I'd put in an application like that. Yeah.
There'll always be another round.
Stewart, on that topic, actually, I was looking at just looking at the regional radiometrics, or the government radiometrics, and it seemed to me that there was a difference, a subtle difference in the radiometric signature between Christmas Dome and Clary's Dome and some of the other domes, and that there was a correlation between a stronger overall uranium thorium signature, and you know, what appeared to be more rare earth enrichment.
Look, sorry, Rick, you look. I might have misled you there. In terms of using the regional radiometrics, that you could use total count, you could use uranium, you could use thorium, and it would certainly pick up around about 5 or 6 of those domes that are higher, and they're all the domes that have the agerine clinopyrox in them, and they're all the domes that have the highest values for those critical minerals. So, in terms of leading you into the right domes, radiometrics are very good. When you're actually on the dome itself, position in the dome is very important. The margins of the domes tend to expose a lower lava unit around some of the edges. They're all lava flows that have basically just caked these small domes, and around the edges you get exposures of probably an earlier lava event, and we're getting slightly better grades when we sample those earlier lavas. We're also getting increased grades sometimes within the domes where there's been valleys or structures cutting through that expose probably earlier lavas as well. So radiometrics are very good, but they don't actually tell you, they're too coarse at this stage to tell us just where the best grades are. But certainly,
yeah, I will add to that what we, and I didn't sort of show all the things that we did, but you know, as I said, we see quite different radiometric signatures in the different domes, but we don't have any geochemical data to understand them. So I think it could be an interesting story, because we don't quite understand why we see such domes being so distinctly different radiometric signatures. But obviously it wasn't the focus of our study, but you know, it could be something that later on, as you get better data, it'd be interesting to compare it with your results.
I think I could guess where your best one is, but you know,
it's already been sampled. Ross is already out there with this.
Oh, we still have more questions. Dave Purdy from GSQ, who's working on our rare earth volcanics project, he would like to know, what is the geometry of these bodies? Are they laccoliths? And what is the level of erosion? Because that'll be important to know before any drilling, and geophysics might help, he says.
Okay, look, I think they've virtually had no erosion. They're not laccoliths. They're actually small finger-like domes that have pretty much vertical edges to them. You can see basically subvertical faulting around a lot of the dome margins. So they're all small. One of the things that we think is different with these domes to Round Top in the US, which is a laccolith, is that they're all very small, discrete domes, and they're all 1 to 2 kilometre in diameter rather than 30 or 40 kilometres across. So they're geochemically somewhat similar to Round Top in the US, but physically they're quite different. I don't know if that really answers your question or not, Dave, but there's no erosion, and I fully expect that when we drill these things, they're exposed above the general background of a couple of 100 metres in height, and I suspect that when you drill them 200 metres down, they'll be exactly the same, almost like a vertical cylinder. I hope to be proved not. I hope I'm not proved wrong. Yeah.
All right, one more question from Nick, and we do have a couple in the chat, and then we better move on to Greg, who's waiting patiently. And I thought I saw that Matt Heindel had joined us again, but all right. So from Nick, he says that PXRF works well for high yttrium. And works well with heavy rare earths in Brown's range, but mostly from a strong association with xenotime. What is the most abundant of all the rare earth minerals at Peaks Range?
Okay, well, look, we're using a Vanta PXRF, which is pretty modern machine, and it's been, I guess, calibrated just for this particular project. And look, we don't get too many of the heavy rare earths other than yttrium, and we've done quite a bit of comparison work between the lab results for yttrium and the XRF results, and I reckon that they are almost all within 5 or 10% of each other. So if we take a pulp back from the lab after we've got their yttrium result and we pass it across our Vanta, we get virtually the exact same result, which means the lab's doing a good job, and also the XRF is doing a good job. So it doesn't get much in the way of the other heavy rare earths, but we get lanthanum, we get cerium and neodymium, praseodymium, and things like that with our portable XRF. So we're getting around about 4 or 5 elements that are useful in actually then deciding which samples we want to send off to a lab.
All right. Now, Michael Amberg, he's put a question in the chat. Remember, you've got to put them in the Q&A, everybody. So he was saying regarding your arsenic solid solution, he thinks it's probably an analytical artifact. Heavy rare earths are very commonly misidentified as arsenic by common EDS software, so there's probably no arsenic, which is good for you. So I guess that's more of a comment than a question, but I don't know if you want to comment on that.
Look, yeah, arsenic sulfide values in these rare earths are very low, and these lavas are very low. Arsenic values are very low, so unfortunately we're probably not going to find any of Helen's gold mineralisation in this area either. But yeah, look, this is work that the CSIRO did where they had that coronadite mineralisation. So I don't know how significant that particular mineralogy is. I think most of the rare earths are really only worth around between, at the moment, rare earth prices are going bonkers. So when we started off on this project, the rare earth value of the project was probably about 12%. Now maybe it's 15% or more. One of the significant things about the rare earths is, though, that they look like they're going to be easily extracted by a relatively cheap processing technique. So even though they're not the highest value mineral, which is really the zirconium, the hafnium, and the niobium are really the most valuable metals, particularly the zirconium and the hafnium. They're going to be much harder to extract by acid leach.
All right. Well, that's generated a lot of discussion, Stu, which is great. And I think that there are some great synergies as well between the Fletcher's Oil project and this one. So, I'd encourage you to talk to each other. And
Look, I think, yeah, Fletcher's Oil is very interesting. And I must admit, when we applied for the Peaks Range, Carl, Ross and I discussed some of the anomalies at Fletcher's Oil. We didn't go and look at them in the field, and the ground was open at the time, and I've pretty much regretted it ever since.
So okay, isn't it?
Yeah, look, in the geological mapping, Fletcher's Oil is mapped as a slightly different volcanic rock type, so per-aluminous rather than per-alkaline, and how good that geological survey mapping is really the question, I guess.
Always can be verified. All right. Thanks so much, Stu. That was really great. So if you want to unshare your screen now.